Okay, well, as people are coming in, I think we're going to get started since it's just after 9 o'clock. Good morning and welcome everybody to CFD Impact 2023. It's been a few years since the last time we did this. I think it was 2019. We had Professor George Kaniadakis here as our keynote speaker right before COVID. And we're happy to have started it up again and get such good support and such a nice program to share with you today. So before we get started, I want to start with clicking this thing here. Why is it not clicking? Hold on. Well, too many fireworks. Yeah, I don't know, but I want to start with thank you. That's what I want to start with. So first of all, I already thank you guys for coming this morning, but I want to thank our sponsors this year. We have a very nice group of sponsors. Raphael has been sponsoring this conference since we started it 5-6 times ago, and we really appreciate their support. And they're coming up to the conference and hiring our students and everything else. So thank you to Raphael. ANSYS Israel and ANSYS National actually is also co-sponsoring this event. They have a booth outside. We're going to be here all day running their ANSYS Fluent software, GPU accelerated on their laptops and their GPUs, and they're going to be running a hands-on tutorial later this afternoon. So that's something to keep an eye out for. GPU acceleration is a big theme of this conference. Without NVIDIA and their GPUs and their support, we would not be here today. So thank you to NVIDIA for also co-sponsoring. Quantum Machines is going to be here later today, they are also a co-sponsor. We'll talk about why that is a little later. And Harel, who works with NVIDIA and supplying GPUs, is also a sponsor. So we thank all the sponsors of today's event. And also want to thank Shimrit, who works in the faculty, who helps with organizing all of the logistics of this meeting. And I don't know why oops, there it goes. Hold on. Whoa. Why is it not? Hold on. Okay, so you've all seen the program, I think, from the website. If you didn't download it, here it is. But we've got a full agenda for today. We're going to start with our keynote lecture, who I'll introduce in just a minute. And then we have a series of talks from the CFD lab. Common theme being GPU acceleration and high speed for this year. That's one of the main themes. And then we have lunch, full catered lunch for you today. Thanks to our sponsors again for enabling that. And during the afternoon hours, we have a couple different talks. One from ANSYS on, again, GPU acceleration of their commercial CFD code. I'm going to talk a little bit about quantum computing and CFD. And then we have a couple more talks in the afternoon and ending with a guest lecture, which is going to be delivered by Zoom by Ricardo Benuesa on machine learning and CFD, another very important topic these days. And then, as I said, the hands-on tutorial will be at the end. Okay, it's working. So last night we had a nice dinner at BP in Horeb, and some of the guys went home already, but this was who was left. It was a lot more fun last time when I used to drink. I don't drink anymore, so it was not as fun for me, but it was still very pleasant and enjoyable. So this is from last night. We enjoyed Neil and I meeting and all the students. And that brings me to our keynote speaker, who's going to start in a few minutes here, Professor Neil Sandham. So first of all, we're grateful to him for coming across the pond, or 2 ponds, I guess, to join us just for this event. He's going back, I think, tomorrow. So he came in special. And Neil is a professor of aerospace engineering at the University of Southampton in the UK. And his expertise, he's been in this business for a long time, longer than I have, in direct numerical simulation and large eddy simulations of turbulent flows. In the last number of years, he's been working a lot on high-speed flows, and he's going to talk to us about that in his talk, which I'll show you the abstract of in a second. But some interesting things about Neil, I went back and did a little bit of digging, and his PhD was with Professor Bill Reynolds from Stanford. He got his PhD in Stanford in the late 1980s. And I remember as a student studying this report from Sandham and Reynolds from the Air Force Office of Scientific Research. numerical investigation of the compressible mixing layer. And if any of you as old as I am and were working in CFD, you recognize these types of wire plots that we used to make. It was not easy to do 2D simulations and 3D simulations with the computer resources. And then, the most recent paper just appeared on studying sidewall effects on shock trains. And you can see the evolution of the field over the 30 or so years since he had his PhD. So it's really an honor to have him here today. This is the title and abstract of his talk, Unsteadiness of Shockwave Boundary Layer Interactions in Transonic and Supersonic Flows. I know that's a topic of interest to a lot of you. And with that, I'd like to invite Neil for his keynote lecture. It should be working. If not, you can the old-fashioned way. Let's slide that. Yeah. Let's do this. And it should work.
Okay. It is working. Right. Well, thank you very much for the invitation here. I've enjoyed my trip so far. Thanks for hosting the dinner last night. It was very nice. And looking forward to an interesting meeting today. So I think going back to the PhD, I think within the first year of a PhD in Stanford, I'd done TVD schemes with Helen Yee, and they were in competition with the emerging compact finite difference schemes that Sanjeeva Lele was developing at NASA Ames. And I switched between the two. And I've since switched back again on various combinations of these different numerical methods. But within the first year, we've already looked at some of these quite interesting developments in schemes. And I suppose most of the work has been doing unsteady, high-resolution simulations of transition and turbulence. I suppose my emphasis has been more on the physics than on developing numerical methods. But of course, you always have to tweak the numerical methods as you go through these problems to find what's good for your particular problem. So I'm going to talk about some of the transonic and supersonic numerical simulations. So we'll do fully supersonic shock reflection problems, and we'll do some of the recent transonic buffet. But I'll throw in some of the things that we're doing that are more sort of computer sciencey or more sort of CFD methods as we go through the talk. So this is I have some thanks to make. So David Lusher has been a guy working on developing the code over the recent sort of 5 years or so. So actually, Jamie was involved in getting this the code system together, and then Marcus Zauner and Pradeep Moyes have been people doing the big simulations of transonic buffet, and our support comes from research councils and also sort of European supercomputer centers. So why shockwave boundary layer interactions? Pointer works. So here's an example of a shock reflection problem. So we have various canonical shockwave boundary layer interaction problems that we like to study in this area. I like to do things that are a bit more complicated than channels and decaying isotropic turbulence, but not as complicated as real applications. So here's a sort of generic application. We have a shock generator up here that generates an oblique shock wave with a certain strength determined by the shock generator angle. This then sets the pressure jump across the boundary layer. If that's high enough, we get separation with reverse flow near the wall. And then we're interested in the interactions of the developing compression waves, the strengthening waves, and reattachment shock waves, and how these influence and are influenced by the separation zone in the boundary layer. So why is this still relevant to external aerodynamics now, not considered a solved problem? It's all to do with the unsteadiness of this. So particularly underneath the separation shock foot, the point labeled S here, what you find practically often are very large amplitude, low frequency oscillations, and these then have important structural impact on your vehicle design. But you then have to take account of the large unsteady loading that can come at this point. If you bump up the Mach number a bit, then you're going to have heat transfer problems, and the whole thing could be fully laminar. Okay, if you're in the re-entry problem and you're coming through the high atmosphere, it starts out being laminar. You go a little bit further to lower density to higher density at lower altitudes, and then you go through a transitional stage, and then you come down to lower altitudes, and you end up fully turbulent. So So you can see all these types of interactions. So we're usually doing all three: laminar, transitional, and fully turbulent interactions that we want to do, and we're interested in the unsteadiness, the shock separation, and the central heat transfer aspects. So I have to plug this on the computer. This unsteadiness is not fully understood yet. So there are many active phenomena. So if you go back through the literature, there's 50 years plus of research in this area. And if you look in, particularly if you look into numerical simulations, you will find interesting phenomena. And the question is whether they're actually connected to the low frequency unsteadiness or just sort of a byproduct of the unsteadiness. And it's current research is really to find out what the essential mechanisms are. What can we filter out as being sort of a byproduct of the fundamental mechanism? What remains that we can then use to model the flow, and also where can we apply flow control? So it makes a big difference if the mechanism is coming from upstream fluctuations in a turbulent boundary layer, or if it's coming from downstream, or if it's all contained within the separation zone itself, and still whether you can then do flow control with this. So what I'm going to do in this talk is give you a little bit on 3D shockwave boundary layer interactions and buffets on aerofoils. I just missed a little bit there. Oops. Let's go through this slide. There we are. Right, there was a little bit extra came here. So in terms of CFD aspects of what I'm going to talk about, there'll be a use of error estimators, which comes into how we do our large eddy simulations and how we design our grids when we go into more complicated problems. So I'll talk about that later. I'll start off though talking a little bit about automatic code generation. So this is a project that we've had over the last few years. And it's to do with most places around the world looking towards exascale computers as the next step in capability. We're still wondering exactly what the architecture is going to be for that. And we have to take account of the fact that things could change as we go forward over the years. We need codes that can cope with different aspects of this move to exascale. So we're probably going to have some mixture of CPUs and GPUs. We can expect other changes in architecture. We start to worry about some of these other aspects. So energy efficiency is really important. Tolerance, if you're running on millions of separate processors, what happens when one fails? Do you lose the whole job, or how can you recover from that? Data compression is a big problem, so we can't actually transport all the files now back to our local machines for post-processing. We have to do, we will have to do almost everything in the simulation as it's running, and that includes doing the graphics. We don't really want to have to port our codes to every machine as it comes along, because things could change quite rapidly. Very well, okay. Let's go back to where we were. Right. So the ideal is this idea of a separation of concerns, that you as a PhD student or a postdoc working on this, or somebody in industry, you shouldn't have to be an expert in formulating the equations for your problem, doing the numerical method, and doing the optimization on the parallel machine that you're to use. So the idea is that we maybe design a system where at the front end, the user designs the overall problem. They set the equations they want to solve, they set the boundary conditions, they choose the basic numerical method. Somewhere in the middle, the numerical analyst then develops the numerical algorithm. And at the back end, we put the computer scientists at the back here, they're the ones who do the optimization of this for the particular architecture. So people who are interested in developing optimal algorithms for different architectures would be working on the back end. So some time ago, we started looking together with colleagues who were then at Oxford, now spread around a bit. This time Reggie is in Hungary, Gihan Mudliger is now in Warwick. We started looking at ways that we could use this Oxford parallel structured system. This is a way that we can then write C code, or a special form of C code, that then they have the software that then does the translation to back-end architectures. So you can then do the same source code then works on GPU machines or CPU machines, and they will take care of that final step. What they've demonstrated is that they could get extremely good performance out of this, as good as handwritten code on the back-end computer. So this is an attractive system. Not the only way of doing it. There's possibilities. So you have to give the OPSC, let's call it, enough information that it can do a good job of optimizing. So every little loop, this is just something that's doing an average of the +1 and the -1. This is the relative positions in a stencil. This is doing half of the +1 and the -1 and putting that into a new. You have to have all this extra overhead of writing this code that tells the backend how to do the optimization. So we were too lazy to do this. This looked like a lot of work to write very long code. So what we then looked at was putting on a front end onto this, and this was just as Python was coming out with symbolic Python. So what has developed out of that is kind of an ongoing experiment that we've called OpenSBLI, which is can we come up with this sort of separation of concerns idea where the user writes front-end Python, then that gets translated with symbolic Python into the OPSC code, and then that gets translated into CUDA or into the lower level code, so MPI or CUDA, that you can then use to run your cases. So there've been a few versions of this. I'll just explain the basics of them here. And you have various things you have to do within the system to define governing equations, boundary conditions, decide on your temporal scheme and spatial differencing schemes. And it was a way of going in and comparing lots of different finite difference schemes, lots of we know, T-know schemes without having to do a lot of painful coding with that. So this has continued through a couple of iterations. There was the original version, it was without shockwaves. There was the second version, which included shockwave interaction problems. And then currently we're looking at what can we do with this kind of framework to get us to exascale computing. Okay, so here's an example of what you actually do as a user at the front end. You're defining your governing equations. So here's the continuity equation, d rho by dt, okay, minus the derivative of rho uj with respect to xj, and that gives us our continuity equation. Okay, go through the same thing for momentum and energy, and you've done your equations. The symbolic Python takes care of expanding this with the Einstein subscript notation, and that then gives you a code, and you've represented your governing equations like this. So this would then be an example of using this system to do a simple test case, Taylor-Green test case, where you have a breakdown of a simple initial flow in a triply periodic box down to small scale turbulence, and you monitor the entropy integral over your simulation, and then you refine the grid until you get to the right solution, you hope. This was compared to a spectral solution. There's another version of this, which is a bit more interesting, is a high-speed version of this. So if you bump up the Mach number of this, then you will get chocolates forming within the Taylor-Green problem. And that's another challenging case for doing within these numerical simulations. So that's one of the things we've been working on recently. The other extension that's come recently is a thing that I guess quite a lot of people have been interested in around the world is doing hypersonics. So if you go into a high-speed flow, you have to extend your governing equations. We need separate species equations. We have to add in diffusion terms. We have to add in chemical reactions. We've got vibration energy and non-equilibrium potentially, and we have the relaxation back to equilibrium terms. Okay, and we have chemical source terms coming into the vibration equation. So there's probably more of these boxes on here. Oops. So the nice thing about the system here, that writing this in Python originally, is actually it's still quite straightforward to write down the governing equations. Okay, you just have to fill in extra transport equations. It's just an extra few lines in the source code, and then you can use the symbolic Python to generate all the equations. So the job of actually generating code has been quite quick with this system. Debugging it has then been a different matter. So the debugging is where you do need people who are not only experts in the generation of the equations at the front end, but can also look at the numerical methods. And then occasionally we might find bugs in the back end where we have to talk to computer scientists to get that working. So it's not a panacea here. But here's an example of a sort of high-speed sort of thermochemical non-equilibrium example. So this is back to these simple mixing layer problems where I started a long time ago. So this is a simple roll-up of a single vortex in a temporally developing mixing layer. So it's streamwise periodic. And we trigger the Kelvin-Helmholtz instability. In this case, we start with very high temperature, 4,000 Kelvin in both streams. And the roll-up of the vortex creates high temperature regions. So the region in the braid here becomes very high temperature. And what you will then find is that you'll then get non-equilibrium effects coming in. So in this case, the core of the vortex came down to low values of vibration energy. The braid went to high values of vibration energy. If you look at the non-equilibrium, it's actually the difference between the rotational translational temperature and the vibrational temperature actually comes in during the entrainment process as the flow is heating up, and the vibrational relaxation is lagging behind. It means the vibration temperature lags behind the temperature rise of the entrained fluid. And here's some chemistry going on. So this was a case that started from equilibrium. And because the core of the vortex has gone down in temperature, you've actually recombined oxygen atoms into molecules within the core of the vortex. So this is kind of where we're going with our hypersonics, and that's kind of been enabled to some extent by using this code generation framework. So a bit more on physics of shockwave bound layer interactions, and I'll get onto more numerical methods. So we have a basic test case, which we call the Katza test case, which is a Mach 2 shock reflection problem. Katza came through DLR sometime around 1990 and set up this 2D test case. And we're going to take this through some unsteady effects. So I've already shown previously some of the features of this. So it's often common to do plots like this so that we can see the separation bubble, but you have to mentally then unstretch this because this has been compressed in the X direction and stretched up in the Y direction. The actual separation bubble in a 1-to-1 aspect ratio looks like this. So they're very long, very slender separation zones. You've got the recirculation vortex is down here. That's where the flow has the negative velocity. That's where the maximum reverse flow is located. We've got a sonic line. That's the chain dotted line here. And the incoming shock wave will penetrate through the boundary layer until it gets to the sonic line. The waves will bend as they go through a region of decreasing Mach number. And then there'll be, in this case, there's an expansion plan that reflects off the sonic line. Those lines are bent as they go through the shear layer, and then you get the expansion plan coming off the back. But you kind of have to remember that this is a very distorted picture of the same phenomenon. Was it pressed twice? Maybe I'll start using the. Oh, hang on. The name of your computer is already on the network. Oh, sorry, I have to look at my phone here. That's why it's not working. Sorry, it's working. Right, so some quantitative things that we can show about this. So here's the displacement thickness. So this is the thickness measured. Momentum thickness is approximately constant through an interaction like this. The displacement thickness follows a triangular shape, so a straight line region on both sides. What's the apex? There's a linear theory that you can do. This is just the standard supersonic thin aerofoil theory. We call it the accurate theory, and we teach this. And these are the symbols on this plot here, showing you what you can do with linear theory. And you can work the linear theory from the front towards the center of the interaction, or you can work it from the back again towards the center. And there's a little bit in the middle where it doesn't match, but you can do the separation and reattachment regions with the linear theory. And this then is the basis for the free interaction concept, that the structure of a separation zone is independent of how that separation is triggered. So you can get separations in different contexts. Let me move on to carry on. So I'm going to do some unsteady work now. So that's the basic test case as a 2D steady flow. We can then put in forcing. So here is some simple forcing put into the density equation. It's like an acoustic source, simple source set in different regions. So we can put it upstream, downstream, or in the middle. And I'll just show you some examples of what you get if you try and force this shock-induced separation bubble with different frequencies. And there's been a whole study of different locations as well. So if we force it upstream, but relatively high frequency, Struwell number of 1.3, where we base the Struwell number on the distance between separation and reattachment, then we get a response downstream, which is in the form of alternate low pressure regions that are moving downstream. This is a shedding mode of the bubble. So you put it in forcing upstream and you develop some vortex shedding within the bubble. Okay, that's something that we know about. This twice. Okay, if we put in a low frequency, so now Struwell number of 0.013, and we put this internally, this is where it's most effective at very low frequencies, then we get what's called a bubble breathing mode, and that's where the pressure is a function of time. So because there's a very steep gradient of pressure near separation and reattachment, then we find that the local pressure either increases or decreases, depending on whether the shock wave is moving forwards or backwards. So if the shock moves forwards, it means the point we're looking at is in a region of high pressure, when the shock is foremost, and this will be where the shock is further backwards, and the reverse of that happens at reattachment. So what we see is that these are approximately out of phase, and that means what the bubble is doing is it's alternately shrinking and expanding. Okay, when we look at very low frequencies, this is something that's been seen in experiments. So the researchers in Marseille, for example, do experiments at 2.3, and that they will document this breathing mode of the separation bubble, and that's what you get, particularly if you look at internal forcing. If you put the forcing upstream, you won't see anything at high amplitude as this. Whereas vortex shedding is something that comes from upstream. So what you can already do in 2D is start to separate out the things that are maybe contributors to the physics of these problems. Okay, so is it internal mechanism that is driving the low frequency unsteadiness? Okay, or is it the upstream? This starts to shed some light on that. Okay, so a more complicated case. So this is now 3D duct flow. So we have now side walls in the problem. We've got a bottom wall, and everything is turbulent from the front onwards. There are lots of experiments and lots of numerical simulations, but this will be the first wall resolved large eddy simulation, let's say. So we're throwing in enough grid points to be able to resolve all the near wall regions, but we're probably still a factor of 2 away from a direct numerical simulation in all directions. So these are still technically large eddy simulations, but they're approaching what you would get with a direct numerical simulation. Okay, so what I'm going to show you some results of are the results of a long aspect ratio 2. I'll show what that means in a minute. Case where we ran 23 periods of the expected low frequency. So another issue of these simulations is just the sheer length of time you have to run to get a good statistical sample of your low frequency oscillation. And we're interested in Struwell number. So Struwell number here is the frequency times the reference length. Okay, the distance between separation and reattachment divided by a reference velocity. And there were experiments as well. So effective aspect ratio. So now we're looking at contours on the lower surface. That's our test surface on which we're impinging shock wave. And if you do it in a very narrow duct, so this will be one of the walls here, and this will be the other side wall. This is our main flow coming along, and there's a shock generator sitting above that generates the shock wave. We get a very narrow region of separation. That's the dark contour here. It shows where the reverse flow is. And we also have contours of pressure shown here. As we increase the aspect ratio to 2 and then to 4, you'll see that the center of the separation becomes more two-dimensional like. But you have to go to very high aspect ratios before you get back to what a 2D simulation would give you. The region near the wall actually doesn't change very much. So if you just focus on the region very close to the wall, then that region has stayed fairly constant as we go through the changes. So the actual corner flow is not so sensitive to aspect ratio, but the overall flow is sensitive to aspect ratio. Okay, here's a separate view of that, and you'll see there are distinct regions of separation. There's a corner separation here, and there's a central separation. So we've got a main separation, we've got a corner separation. We have power spectral densities. Let me just show that one again. So you now take all this data, you've got time series of pressure data on all the surfaces. You then Fourier transform that, you do your Welch algorithm and figure out what's going on in spectral space. And what we find out is, so the vertical axis here is going in the x direction through the interaction, and we're showing contours of the power spectral density as a function of straw number in this direction. So what pops up at separation, close to separation, is this very low frequency and high amplitude fluctuation. So that's the separation unsteadiness. This is the turbulent boundary layer that comes in from the inflow. We'll go for the standard turbulent boundary layer spectrum here. That goes through big distortion in the separation zone and then starts to reform, but as a thicker boundary layer downstream of the interaction. And then what's interesting is then what happens to this in the sidewall region. So now we're looking, this is now in a plan view, and this is at straw number 0.03, so this is the low frequency that we're interested in often. And this shows us the main area of low frequency across the core of the channel, but then we pop up these little regions of low frequency in the corner region. And what we've been interested in is whether that is connected with whether the corner separation is connected with the main separation. Because we've got these two different separation zones. They both have low frequency. Okay, but are they kind of in phase with each other, or are they kind of independent? Remains to be seen. These were experiments that Paige Raby had run at Imperial College that showed similar structure, although they weren't able to measure into the corner regions. This is then along this red dashed line here. We take a slice and look at the power spectral density. Then we've got quite a big peak at reattachment and another peak at separation. So this is another case where there's a bubble. And if we look at our analysis of this, so we did 2-point correlations and with different locations of the original point. Speed up slightly through this bit. Okay, so when we've got 2-point correlation where we get regions that are out of phase, then that corresponds to a breathing mode. We saw it before on the low frequency response of the separation bubble. So where we've got the red regions here, this is our reference point, and then we look in this case downstream. We've got a breathing of the separation bubble because this is out of phase with this one, and we also see the same thing in the streamwise direction in the corner part of it. So what we were able to say from this piece of work was that the sidewall vortex is the unsteadiness of the corner vortex is not connected with the unsteadiness of the main vortex, even though they're in the same view. They're not actually correlated with each other. They're independent separation zones that are developing. Okay, so now I'm going to switch to the transonic bucket. So we've got 15 minutes or so. So transonic bucket is another example of a high amplitude, low frequency oscillation. Okay, but we're going to come back at the end of the talk and look at the differences between these two. You can find global modes in RANS calculations, whereas you can't for the shock reflection problem. So this is an example of a globally unstable flow as found in RANS. So Crouch and Timmer will be two of the names to look for in global modes of these kinds of unsteady transonic flows. So transonic, we have more communication. We have the possibility of sound waves going around the whole aerofoil configuration. So something from the trailing edge would go all the way around the aerofoil, whereas when we have a shock reflection problem, everything is supersonic and we don't get any, we don't get as much upstream influence. It can only go through the boundary layer. So I'll talk a little bit about methodology and a little bit about some of the results. So this is now back to our original code. This is the classic code, the Fortran code, and the numerical methods are a bit classic as well. So don't regard these as being particularly new now, but at the time, I think we hit on quite a nice combination. So these are explicit codes. They are high order, although fairly early on, we'd observed that we didn't get much benefit going beyond fourth order. That comparing fourth with sixth order, we didn't get much benefit when we had shock waves in the flow. So there was an influence of the shock wave in determining sort of how high an order we should go. So anyway, fourth order, if that's high to you, then we're doing high order methodology. The time advanced scheme is just third or fourth order, different variants with very similar results. We were doing a splitting of the Euler terms. This is the entropy splitting, was one of the earlier attempts to try and obey a nonlinear stability criterion. So you could, for scalar conservation laws, you could prove a nonlinear conserved quantity, and that showed some definite benefits compared to doing fully conservative methods for these sorts of problems. So obviously, since then, there have been lots of other splittings proposed. We've probably not reached convergence, but this was an early case of an entropy splitting that led to some enhanced nonlinear stability. We were doing a hybrid method. So in this case, we had a TVD shock capturing scheme, but we were mainly trying to hit the high order. So we would have our sort of fourth order central was applied everywhere. And then in this formulation, we would then apply TVD step as a filter at the end of every full time step. And that's not only efficient, because you're only doing it once for every sub-step, you're doing it once for every full step. But also it's quite effective when you combine it with lots of limiters. So we ended up using two limiters. One is one of these Harton limiters, so compression method from Harton that have been tested in this early paper based on characteristic gradients. And then we add in the Ducrot sensor, which is one that turns off the shock capturing in boundary layers. So what these two limiters, two sensors are doing, one of them is turning off the shock capturing in boundary layers, and the other one is turning it off anywhere away from shock waves. Okay, and the combination of those two meant that you're only corrupting the flow with your first order treatment around the shock wave, and then you are able to get some benefits of high order everywhere else. And I think this is kind of backed up by some recent work as well. I think sort of the recent work of Yi has been showing that if you think you're upgrading this TBD scheme to do different types of WeKnow of different orders, and actually it doesn't get any better with higher order WeKnow. In fact, you're better off doing a lower order method, and you get you're not wasting time doing high order WeKnow. You might as well do so I think we'd hit on quite a good combination at the time. There are bits that could be improved, but it's been extended to curvilinear body fitted multi-block grids in the intervening years. What's slightly new here is the use of spectral error analysis when we get to doing airfoil grids. So we're trying to design our methods for doing airfoils, and we're trying to do large eddy simulation, and so there's a big new variable is how you design the grid. Okay, and what we did here was kind of borrowed a bit of an idea from spectral element methods and discontinuous Galerkin methods, where you have access to all the spectral information within all of your elements. And what we tried to do here was do a finite difference version of that, where we break our domain into little sort of 32 squared or 32 cubed elements. We do Fourier transform to find out what the local spectrum is doing. And then we make use of the fact that we know how our method fails when it's suffering from low resolution. We know that we get grid-to-grid point oscillations, because we don't have other methods particularly to kill off grid-to-grid point oscillations. So if you know the way your code is going to fail, you can use that to help you tune the grid, so you've got enough resolution in the regions where you really need it. And then we've extended that to do an LES method as well. So the grids that we're using, okay, so horrible sort of structured grids in with multi-block formulation, and we have usual sort of characteristic boundary conditions around the far field. So there's nothing very interesting there. But the way the code fails is that if we look in the spectrum, we'll see a turn up of the spectrum at high frequencies, high wave numbers. And if we know that that's happening, then the idea is to figure out where that's happening and then flag up that this region is under-resolved. Okay, so we've not got at this point, we've not got other filters in the problem that are taking out those oscillations, and we don't have a numerical method that naturally takes out those. So we're trying to detect those sorts of oscillations. And we just flipped over 2 slides. So we can do that without doing an entire Fourier transform. So we work out our Fourier coefficients by direct convolution. So you can just you get the grid to grid point mode is this one, which you can just get by summing up -1 to the grid point j over your domain. You can work out the one that is kind of 4 points per wavelength and 8 points per wavelength. And then we can look at the spectrum and then see if this is decaying at a rate that we would like. So we have this little r in here is the rate at which you think your spectrum should be decaying. If it's decaying fast, then that's good. And the A2 will be smaller than A4. A4 will be smaller than A8. A2 will be smaller than A8, and everything is decaying nicely. This floor symbol here is like an integer truncate in the code, and that means that we would come out with 0 for this if we were in what we think is a well-resolved region of the flow. If your spectrum starts to turn up, then these numbers here turn into ones or even higher, and that then puts up this indicator function to higher values. So we've got sort of a way of extracting relatively cheaply where the regions are that are under-resolved in the flow. So then you can color code these. This is actually now gone to the next step where we have a filter that's then tuned on this method to then only put filtering in where we detect that there is this upturning of the spectrum. So this is the attempt to get this into a large eddy simulation. So then you can, a posteriori, you can then check how often your filter was actually active. So then we have regions with no color where the filter is not turned on at all. And then we've got regions here that are sort of blue, green, and red. So red means that you're having to apply this filter frequently within your code. If it was a direct numerical simulation, then we wouldn't have any of these other colors. So that's kind of been the use of this. So 2 uses. One in designing the grid. So you just iteratively run a simulation, tens of thousands of time steps, but not to completion. Check where you're under-resolved, refine the grid in those regions, do it again, and then iteratively you would get your grid sorted out, and then actually run the simulation with this filtering and see how much filtering you're having to do. There are a few validation cases. I think the interesting one is the comparison, first of all, with a previous simulation by Dandois in Onera. So this was the green line was this is again a spectrum. The green line was done by Dandois, and he found this peak here, which he called transonic buffet, laminar buffet. This is a laminar flow aerofoil where we have transition to turbulence during the interaction. If you look, his green line stops here. So you haven't run the simulation very long. If you run it long enough, you then pick up another peak here at low frequency. So what he was calling here the laminar buffet actually coexists with a much lower frequency, which turns out to be the same physics as a turbulent buffet. So we have essentially a problem of terminology. This was the comparison with some experiments that Marcus Zauner had run. So he did these simulations. He then did a postdoc in Onera, and he managed to convince them to do some experiments there. And one of these is simulation. This is the simulation, and this is the experiment. the Schlieren picture, and you've got this is a case where we have multiple shock waves because it's a laminar flow upstream. We have multiple regions of shock expansion, recompression, and so on. A bit like shock train in this case, and we get the same phenomena seen in the experiments. And I'll show you. Is there anything else to say there? So there's agreement on the spectrum, and there's agreement with the experiments. So a few results just in the last couple of minutes. So interesting things. So these laminar flow sections are supposed to be sort of next generation commercial aircraft with lower drag, right? So the idea is, can you go from current fully turbulent configurations with a relatively well understood shockwave boundary layer interaction? Can you then make these into laminar flow sections where the transition process happens alongside the shockwave? Okay, but the whole thing is potentially quite a lot more unsteady and a bit more risky. You don't want to go into that sort of go beyond this sort of buffered envelope. So the idea of these studies was to look at force versus free transition. And there was also an opportunity to look at some sort of data-based analysis of the different modes that come into these simulations. Okay, and we're still interested in other modes here, say intermediate modes. We're still interested in those. So we get quite a lot out of these XT diagrams. So we're looking now on the surface or slightly above the surface. These are contours of dp by dx, and in this case it's just outside the boundary layer. And dp dx, if that's strong positive, you've got a shock wave. If it's negative, you've got an expansion wave. But it will also pick up vortex structures. So vortices will have low pressure, and the vortex structures pass over this sort of line. This is the dashed line here. We're looking at the XT diagram. So we've got our buffet, which is this thing, this oscillation here, low frequency, and that lines up with the lift coefficient, the right-hand side. So the whole, the transition line is moving backwards and forwards with the low frequency of the buffet. The lift coefficient is going up and down. The drag coefficient is going up and down significantly. We've got shock waves into the laminar flow section, and we have multiple shock waves coming off. So this is, we're also as well querying some of the modeling of this, because all of the modeling assumes you have a single shock wave that then moves upwards and moves forwards and backwards on the aerofoil. Okay, and the shock wave is considered key part of these theories of transonic buffet. But if you replace one shock wave with three shock waves, as we got here, and we still got buffet, okay, then clearly the shock waves the single shock wave is not critical to any mechanism of buffet. And in fact, we can take away the shock wave completely and still get a low frequency oscillation, suggesting the shock wave is really a byproduct of buffet and not a necessary thing. Other things we've got here, we've got, if you look very closely, you can detect Kelvin-Helmholtz instabilities. We have a separated shear layer in here. If you look very carefully, you can see Kelvin-Helmholtz structures. What we're seeing here are larger scale structures that are being shed from the back of the separation zone and then merging and continuing downstream into the wake. So we've got lots of modes at different frequencies to consider. This shows you some idea of the unsteadiness of the laminar case. So I think there's a second one with a spectrum. So if we have free transition, then you've got this big high amplitude oscillation. If you then trip that, this is at Mach 0.7, if you trip it, you get the blue. So you can stabilize the whole of the buffet on this laminar flow aerofoil by tripping it upstream. If you shift to a higher Mach number where the buffet is better established, you get the red line. And then if you then force that, you then go to something where the buffet is still present, but weaker. So the problem with these laminar flow aerofoils is the very high amplitude buffet that you get. Here's some examples of high lift and low lift to show you the changes that are going on. So with the free transition, you get at the high lift phase, you get a really large region of supersonic flow. And at the low lift phase, you get a small region of supersonic flow. if you look when you force the transition, then you get a much smaller difference between them because the shock wave is not moving as much during this cycle. Okay, and from the POD, so in this case, so spectral proporthogonal decomposition does pick up different modes. So if we do the spectrum of the SPOD, we get the Buffet mode and the wake modes. So at least two critical modes. Right? The low frequency always shows up, the wake always shows up, and then for different aerofoils under different conditions, we might get intermediate modes that are currently an issue of study because you can get separation bubble modes on top of these other Buffet and wake modes. And these are some pictures of the different cases. This is the pre-transition case. This is the forced transition. And then we've got the different wake modes. So the SPOD has been a useful tool here for extracting information from these very large simulations. Okay, so I've already mentioned we have a naming problem. So laminar Buffet was already found by Dandois, okay, but he found it for a higher frequency, which was it is a separation bubble mode, whereas there is also a Buffet mode at low frequency. So what we would argue is that there is always present this Buffet mode, whether you have a laminar aerofoil section or a fully turbulent section. Okay, but in some instances, you can get this extra mode in the separation bubble. And what can happen in experiments is that you can see that medium frequency mode appearing first. So as you increase the Mach number or you change the angle of attack in your experiment, sometimes the very first lower frequency that you observe might be this intermediate frequency. But if you keep going, you will then see the low frequency emerging at the same time. That's a later time. Okay, so we've got all these different frequencies. We've got the classical 2D Buffet, we've got intermediate frequency, we've got the high frequency, and we've got Kelvin-Helmholtz instabilities at very high frequency, and they're different. So I will just conclude with some of the differences between transonic Buffet and the shock impingement problem that we had earlier. So transonic Buffet, there are global instability modes. Okay, even in RANS, you can do a RANS calculation and detect these global modes. If you do a supersonic shock impingement problem, then you won't find a global mode, at least for these typical strengths of bubbles. So there's no corresponding global mode. Transonic Buffet, we have wake modes and separation bubble. Okay, and they're separate to the low frequency mode. In the 3D duct case, you can have multiple, if you've got multiple separation zones, you've got multiple low frequencies going on, and they're of independent origin. These things will pop up inside any separation zone. Shockwaves seem to be a byproduct of the unsteadiness, whereas the classic theories of transonic Buffet tell you that the shock is a key part of it. It's acoustic waves coming from the trailing edge, interacting with the shock wave, and that forms your sort of a feedback loop that then sets everything going. If you take away the shock wave from that, then the theory is missing a very key component. So a lot of the theories of transonic Buffet are likely to be at least incomplete, not incorrect. Okay, and then for the other case, the shock reflection problem, then we have more of a response problem. It's not a global instability, it's a response to forcing. And then you have to think, is it the upstream, is it the downstream, is it the disturbances inside the separation zone that are important? And this probably changes for different strengths of interaction. Very weak interactions, it can be upstream, but for the majority of cases that we've looked at, it's the internal mechanism that is the key mechanism for doing unsteadiness of shock reflection problems. So that was it. I hope that was a sample of what we've been doing over a few years. So examples of transonic flows, of supersonic flows, and then some of the numerical methodologies that we've had to adopt to be able to do these at approaching direct numerical simulation on quite large computers. So thank you very much.
Thank you, Neil, for an excellent talk. We have time for some questions from the audience. Yes.
I am interested in the numerics, specifically the error indicator that basically flags the area where the power spectral density shows the upturning. So I'd like to understand. So in a sense, that will basically give you the energy content in different frequencies, right? In a sense, right? So and that is heuristic data. That does not give you error bounds as such. So I'd like to understand how does that translate into the decision of going up or high in order. Of course, you will go lower in order in that region, and then how will you refine the elements?
Okay, this is finite difference on a single grid, so there's no elements to refine in this case. If we were doing spectral elements, then we could tune with that. So the two aspects to it is the grid refinement. So we're not changing the order of the method either. Okay, what we're doing is just we're doing H, I suppose you would call it, refinements, that we're varying the grid in between iterations here. So you'd run it on a particular grid, you run the error indicator, see where the errors are, refine the grid in that region, okay, and then run it again and check your error indicator again. Okay.
Every grid?
And then that's in your grid design. Okay, and then let's separate that from the large eddy simulation methodology. So once you've done that and you've got a grid that's approximately right, okay, then you go to running it in the LES mode, where you're also using the error indicator, but then you're adding a filter in. So at this point, you're now trying to kill off the high frequency oscillations, or high wave number oscillations. So now you're adding in a filter, and the filter was done every so many time steps with such an amplitude. Okay, so it is it's a trial and error method. It's not something that you can say is going to work for every problem. You'd have to tune it for different problems separately. So it's been run for the aerofoil case at the moment. But then the idea here was every 30 steps you then throw in your high order filter. So you'd have a high order compact filter that you would put through your flow field, and that would take out some of the high wave number content. Okay, and that's the LES parts of it. So there's no subgrid model here, but there is a filter that's taking out the high wave numbers.
More questions? Yes.
Yeah, you show a framework that you built for compiling Python and CUDA code for running on GPUs. I wanted to ask, is it also running the MPI when you're doing a lot of simulation with a lot of GPUs?
Yeah, you have MPI across the different the GPUs.
It's built in the compiler that you developed. In the OpenPI.
Yeah, it's not the bit that we developed. It's in the bit that Oxford, as it was, developed. It's in the OPS that it has. You can, if you're running on a single GPU, you just generate the CUDA code and run that. If you're running on multiple GPUs, you have MPI interconnection between the CUDA running on the different GPUs. So it's scaling is then depends on your machine, I suppose. So we've been typically running on a sort of a 4 GPU node on a machine in Cambridge, and then we've tried to run it on then one node, 2, 4, 8, and the communications then starts to hit you when you go cross node. Okay,
in case anybody doesn't know, I know the answer to this. The open in OpenSPRI means it's open source.
Open, yeah.
So it is available to download and try. And I guess
the OPS is open. Yeah.
Have you had, do you know of users around the world that are using it? Have they been in touch?
Yeah, we have a training course coming up.
So if anyone's been checking out the software, you can check it out online, download, install it, and you can try it yourself. And be in touch with Neil if you have any complaints, right?
Yeah. So
they send all bug requests to you or no?
No, not to me.
Any other questions?
David Lushing, there we go.
Yes.
What is the airfoil? So, what is the spin size? What is the minimal spin size to capture the phenomenon?
The issue with span size is that it gets stronger the narrower you choose your span. So if you do something that's only sort of 5% of the chord, you get a very strong and a very sort of peaky spectrum. So you lock into sort of the particular mode, and it's very high amplitude. If you make the domain wider, so we've been up to 1 chord in span. And okay, so you still get a 2D. It's essentially a 2D buffet mechanism. Even when we swept the wing, this particular airfoil section, we still got 2D buffeting motion. But it gets weaker as we increase the span. So it changes in amplitude. So you do have to be careful with the span-wise domain size.
We have another question on the other setup. So in one of the visualizations, it looked like a half domain. So I was wondering, you have both balls in there, or it was a half domain?
Yes, we originally used a symmetry condition, and we got some funny stuff going on at the symmetry plane when we were doing a turbulent boundary layer. As you're constraining all the structure, if you think of hairpin structures, you would only get symmetric structures in the symmetry plane, and that gave some non-physical statistics in that symmetry plane. So I think symmetry planes are bad if you're doing time-dependent calculations like this. And then we switched to doing the full width of the channel.
Is there experimental data like PIV velocity profiles to quantitatively compare your predictions to the measurements, or that's too difficult under the unsteady conditions? Or?
That one, they'd only got surface pressure data, so that's what we showed was a comparison with the experiments at Imperial. But they've typically got surface pressure, or they've got oil visualizations, pressure sensitive paint, but they hadn't got, and then you want stuff very close to the wall, right, where they can't get the PIV planes in very close to the wall. You compare what you can, but you don't have very, very complete data.
Any other questions for Neil? Okay, well, thank you very, very much.